fair enough. I think, what, if I talk like this is fine.
Just fine, yeah. And if you wanted to help, somebody over here, the camera will track you and follow you too. Just as long as you keep that microphone close to you, I don't really care where you
That's
go.
fine. Thanks, man.
Yeah, I appreciate it. But yeah, that's perfectly fine. You can kind of hear yourself in the sound system, and as long as you hear yourself up there, then we'll hear
It
you
works.
too. Yeah.
Thanks.
Thank you.
I think we're good, right? your instructions and how to log into the vary, and then you don't have to do so many things. You have to click on an icon that says binaries. It will download from Git all the required files, and then there is already an environment in the vary with the same name, think binaries. So you can use this environment to run the notebook.
What do you think about trying to get people to move forward because we have such small fonts and plenty of seats towards the front?
With this one.
So if people would like, it will just be a little easier to read the screen if you move forward. Just don't get too close.
We have some more. Yeah, you can settle yourself down. Take it easy. It's 4 hours, guys, and we already have a plan 45 minutes break. You can take it easy. Okay, now we have one. So, just to introduce ourselves, myself is Vangelis, and my colleague and friend Gordon. Right. So we are both particle physicists. We are working at CERN. This is the European Lab of Particle Physics in Geneva, in Switzerland. So we came here to do this tutorial, and in our job, quite often, we have to deal with a lot of numbers. And that's the point of what we're going to show today, how to deal with a big amount of numbers, a lot of numbers in Python, in an array-oriented way. Gordon is also a professor in the university nearby in Washington, in Seattle, and I'm a researcher at the Technical University of Munich in Germany. Prepared to come together here and give this tutorial. I don't know, do we miss anything about our history?
I think that was perfect.
Right. So as I said to some of you already, we're going to use the vary today, this platform that is.
Oh, maybe just quickly, we've got two other people who will be helping us out. Anna sitting way in the back, who is a researcher from Princeton, and then another fellow, Matthew, who he's in a meeting
He's
now.
going to come.
He told, well, this is what he told me.
Good.
So we've got plenty we've organized this in a little bit of lecturing, a little bit of projects where you're actually trying to break some code. So during that time, we'll have enough people wandering around if you have any questions. All of us are to varying levels experts.
So yeah, this tutorial has three parts. Let's go a little bit with structure. It has 3 parts, and every part, if you open the directory, every part has a lecture, kind of notebook that I'll be opening here. There is a workbook, which is what you should open to follow some little things and execute some code as I'm presenting and talking. And then part 1 and part 3, they have projects as well. So you find a project notebook that will take some time to work on. There's also a solutions notebook that we will go through together after. So yeah, this is how it's gonna work. It's gonna be project 1, talking and project. Part 1, talking and project. Part 2, it's just talking, no project. Part 3, talking and project. And breaks in the middle to chill out a little bit. Okay, so I think I can start, right? How you feel? Everything is set up? Any question in terms of setting up or no? And we'll have time.
Yeah, and when you do start in Bari, why do I keep saying Bari? Oh, I know why. That is a very old TV show. Okay, when you start, make sure that you select the environment that's called
Right, so we'll start with part one. As I said, I opened the lectures notebook. You open the workbook. It's called workbook. This is what you should open, and then you will follow a few things there. So part one is about a little bit about introduction to array-oriented programming, and what is this about? Of course, it's not working now, but we have this. So it's a sort of a programming paradigm, along with others that you might have heard, let's say object-oriented or functional programming. Maybe if you come from a computer science background, you know this, or imperative programming. We'll compare a little bit, especially imperative programming with array programming, and there are some differences that will show, will make you better understand what array programming is about. So it's another programming style. Yeah, and the basic primitive sort of type there is an array. An array is a sort of contiguous place in the memory where you have numbers. So it's like numbers stored next to each other. That's what I said, like with Gordon in our work, we have a lot of times to deal with a lot of numbers. So this is why this helps us. It's a representation where you have a lot of numbers, usually that might represent the same thing, one after the other. So it's array, right? And what we usually want to do is do operations on these numbers. You want to, I don't know, multiply them or do some more complicated things or exponent or apply a function and so on. And then you do this in a lot of numbers at the same time. That's the basic concept and what we're going to use. Now, I will start clicking the notebook to see if this works in Control Enter. Okay. Now I imported NumPy, and NumPy is a kind of basic tool that most of you are aware. It's a library in Python that is actually doing this thing, a sort of array operations over an array, right? And we'll
just out of curiosity, how many people are, that use NumPy on like a weekly basis? So we've got a couple.
I thought I would see all the hands here, so I need to step down a little bit on my, okay. So some of you have even never used NumPy. Is there somebody that never used NumPy? No? Okay, at least all of you have touched NumPy, but not regularly using it. Okay. Let's see.
Yeah, now you broke it.
Of course.
Want some help? You scroll.
But why I don't?
You collapsed a whole bunch of cells. You're in part 3 now. So
That's data.
I suspect that's part 3.
That's part 1, but
So this is why you gotta. There you go.
let's try again. So if I press.
So never use the left and right arrows.
No.
I know it's completely. Don't ever touch those. Just the tiny little up and down.
Right. We'll see how it's going to go. So I import NumPy, and I said that NumPy is a sort of a very common tool in Python to do this array-oriented programming, right? But I will show you some examples. It doesn't mean that always, if you use NumPy, you do array-oriented programming, right? And for example, here, this is a not array-oriented sort of operation. So we have some input data, right, and some output data. I don't know what's going on. We have some input data, and then what we can do is a sort of basic operation, right? We take the input data, and then we square it. But the fact that we write explicitly this for loop this takes us out of the array-oriented programming paradigm, right? And this is more of what we call imperative programming, when you explicitly write this for loop. So this is going to work, hopefully, yeah, and it's working. You're going to get the result, but you know, this has a performance drawback when you write for loops in Python. And also, you know, you write extra code that you eventually don't need, actually, right? And then I have another non-array-oriented programming example. So in Python, maybe sometimes you don't write the for loop explicitly, but you might do a sort of kind of a lambda operation. Again, you get some input data, and then you can write it in a different way, and you map it. So you say, OK, I want this lambda function. I want each element of this input data to be squared. And then the map is applying this function to all the data, and so on. But still, the fact that you write something that is going to be applied in each element, and you do this map is like a for loop. So this is not, again, an array-oriented programming example, right? I can run it, I'll get the result, but this map here is like doing for loop, right? So maybe what is actually array-oriented programming? So this is a nice example, right? I get my input data, and then I just square it. And because I use NumPy arrays, it knows that it needs to apply this operation in every element, but I'm not stating this directly. I'm just doing it in the whole array, right? And then I can execute, I'll get the same result. So that's an array-oriented programming paradigm, where I take an array, and I think about this as a whole thing, and I just do an operation without caring what has happened element-wise, in a way. You know, I talk a little bit about this programming paradigms, the imperative one, and the array-oriented one, and the object-oriented one, but you know, there is not a very clear line what, you know, if, as I said, I saw some examples with NumPy, which is not array-oriented programming. So I cannot tell you that whenever you use NumPy, you do array-oriented programming. And there is, you know, sometimes the line is not so clear what is each one. But the point is that all of these different paradigms have been made in order to express and emphasize in different aspects of the software development. And for example, in our work, we do a lot of object-oriented programming ourselves because we usually our software is very large and very modular. It has a lot of structure, and this helps this object-oriented programming that, you know, it was a fashion at 90s. You know, it's still helpful to us. And there are a lot of other paradigms that, you know, some of those I don't even know exactly, or I don't have experience as a developer. But array-oriented, where what we're going to focus today, it's especially helpful, as I said, when you have a lot of numbers, and when you want to think about these numbers collectively, right, as a distribution or as a collection, what has happened of this, a lot of numbers as a whole, right, and not element by element. That's a little bit what strikes in array-oriented programming. While this imperative that I think I mentioned already and will mention again today, it focuses on procedure in every kind of element. So when you are in this imperative paradigm, you write a for loop, and then you take every element of an array or a data structure, And then in every element, you're thinking, and okay, in this element, I will do this thing. On the next element, I will do this thing. It's very much based on detail of what I'm doing. Yeah, and there is a lot of there is a lot of history, even from the kind of 60s, where the first array-oriented programming language kind of appeared, this APL, and we used to have an example about APL, but we thought that it's too much history and archaeology these days. And over the course of the years, a lot of other languages that are array-oriented or exhibit some array-oriented characteristics. As I said, it's not always super clear line that this is array-oriented, this is not, appeared. And probably you know some of the very late ones after 2000s, like NumPy and Julia, maybe you know about this. And there is also something that we'll touch today, awkward array. So these are the two basic kind of libraries that we'll deal with today: NumPy and awkward array. Awkward array is going to be on the third part of our lecture, that we're going to abstract a little bit, generalize this topic of array-oriented programming. Okay. Yeah, another thing that has to do with these languages we put there, it's there is a lot of interactivity, and this is especially obvious on today's sort of data platform technology. Just than a bar you do now, what I'm doing now, right? I'm clicking, doing a computation, I get the result back, I'm able to look at this, and then click on the next one. So there is a lot of interactivity on these environments. A lot of these languages were built with this in mind. Even the first one, this APL, I showed, like, it was very interactive language. And all of these they feature what we call in Python this REPL, read, evaluate, print loop, right? This is, every cell in the Jupyter notebook is actually this sort of operation, right? And there is a lot of concise notation, and I think that's the big thing, that all of them are like very mathematical, right? And even NumPy, a lot of times you might have used NumPy, people who have used it to do really mathematics on it, and it's, it's very expressive, and you can clearly understand what you're doing on the mathematics side of things. So, and that kind of makes sense to what I was saying, like, array-oriented is helpful when you have a large amount of numbers, large amount of data, and you want to process them, and that's very close to a lot of mathematical operations and so on. Yeah, but what I said is that array-oriented programming, it's very much, you care about what happens to this large amount of numbers as a collection, right? And not element by element. What happens to this as a collection? So this is what we want to show a little bit now. We can make a data set of kind of normal distribution, right? This is 1 million points. We're going to generate 1 million points. 1 million points is 1 megabyte, right? It's not too much. So we can scale this up a lot if we want. And then what is helpful, actually, I can generate this data set, and I can put this data set into a histogram, which is a sort of object, I would say, that it's helpful to represent a lot of numbers. That's the power of the histograms. When I have a lot of numbers, it's a very compact representation of a lot of numbers. And I can get a feeling of what this collection of numbers is showing as a collection, as a distribution, right? And immediately you can see that, okay, that's a Gaussian distribution, and you know these properties from the mathematics and so on. So that's a nice, that's what we're gonna, keep in mind, that array-oriented programming needs. That's the focus, to see these numbers collectively and do operations collectively and get a feeling of what is going on collectively, right? And then the good things are, okay, that's a Gaussian thing, but what about if I square it, right? I can very easily now see what is the effect of squaring this sort of distribution, and what are how the properties change if I square all these numbers together, right? Maybe some of you could already guess, if you are good on maths or stats, how this is going to look like if I square it. But I can do more complicated things. I can take the inverse of this data set squared and put the sinus, calculate the sinus, and it's not easy to, figure out how this distribution will look like. But then you can very easily get this back from Python or from your with just a few lines, right? So again, I did an operation on this collection of numbers, and I can quickly see the effect as a distribution, and that's what the very deep benefit of this sort of programming paradigm. If you have any question, feel free to stop me, right? I'll take another 15 minutes roughly to finalize this part one. As I said, mathematics and the expression of mathematics are very important in this, and very, people took care of it to be apparent what sort of mathematics you're doing. You saw before, I take the square, I invert it, and then I put a sign on it. It's apparent what I'm doing, right? And then there is also a computational advantage, because I mentioned this at the beginning. When you write for loops in Python, that's a slow thing. And when you have billions of elements to loop through, that becomes like a no-go thing, right? So you need to think a little bit, use the technology, right? Use the technology better to get this computational advantage, avoid doing explicit for loops, do operations on large amount of numbers, and this is what actually this programming paradigm can give you. And you accelerate this loop eventually, right? That you will have to do, like this huge loop. I'll use a little bit more NumPy. So part 1 and part 2 will use NumPy, and then I said in part 3 we'll use some more abstract kind of libraries to do array-oriented programming. NumPy has it's being used, like, I think, heavily in the scientific Python ecosystem. That's a cheat sheet that it's nice to have handy. And the basic concept is, these array-oriented operations in NumPy. And, if some of you might be familiar with these things, some know, so you can keep this cheat sheet help handy on you. And even today, I think today might help you to some things as I see, right? So how you can do these sort of collective operations in NumPy, right? So what is going to happen if I run this thing? Like, I have an array of some elements, and then I have an array of another elements, right? And then I can add them together. So NumPy will go and do this element-wise without us writing an explicit for loop. This is what we gain. We avoid writing a for loop and getting the result of element-wise operation. So you see, if I run the cell, I'll get the result without writing an explicit for loop, and that's the point here. And then the other nice thing is that there is a concept called broadcasting in Python, which is essentially a way to automate. Like, Python is not very strict on types. right? It's a language a little bit loose on what types I move around and what I'm doing with. And sometimes this is annoying. Sometimes I can take advantage of it. So I can write this formula, right? That's a quadratic formula. I can, you know, probably this formula from your high school. And then this takes three numbers, A, B, and C, right? And as I write this function now, this looks like a scalar operation. So I give three numbers, I get one number back, right? This is not array programming at all. Like I give three numbers, I take one number back. That's it. I executed, I think. I don't want to spell check. I want to execute it. I hope I executed it. So, you know, I can do this thing, right? I can give these three numbers and get the result back. Simple as that. But I can take advantage of this sort of broadcasting. I'm not even sure this is actual broadcasting, but okay. I can use this formula to operate on arrays. So instead of you know, giving three numbers in to get one number out, I can give, what is this, a million number. I can make three arrays. Each array is a million numbers length. And I can feed these arrays into this formula. So what I'm going to get back, it's another array of length a million, where each element has actually the result of this quadratic formula without writing for loops. And that's a sort of a benefit that NumPy gives you. You can write a formula, you can write a function, and you can either pass scalar values or you can pass arrays into. When you pass arrays into, you get some computational advantage, you get the result back. The same operation happened in all of these huge arrays. That's what this example want to show you. Clear? Right? So what's happened now? Okay, I wrote this function before. I wrote it in a very compact form, right? I square it and I put some minuses, some sort of multiplication and so on. But what actually happens in the computer is that the computer needs to, you know, NumPy needs to break this down to some operations. So if I would write this quadratic formula pedantically, I'll get something like this. This is what NumPy is doing behind the scenes. It's not it's not exact the same thing, but it's very similar. This is what NumPy will try to do. We'll take we'll take the negative of the b, we're gonna square it, and then multiply with something. That's temporary variables. Then you're gonna delete the temporary variables, go and do some subtraction, square root, and so on. Like, this is a pedantic way to write this formula. And then I can run the same thing here. I can pass arrays again, right? Or I can pass scalars. It doesn't matter. So that's a little bit of a broken down version of it, right? You see, I get the same result. But what we want to show with this example, that there is some performance, actually, considerations on these things. That's why we wrote the quadratic formula in a very compact form, and then we wrote it in a little bit more pedantic form of what is actually happening in the computer behind the scenes. So in principle, these two things should be close in performance, right? As I said, either if I write something in a very compact form, or if I write it in a pedantic form, you know, the computer is going to do more or less the same thing, right? So both of these you will see later that is going to give us very similar performance results. Yeah, this is how we have it. Yes.
Vangelis, in that last one, the pedantic form, is it possible to go back without totally getting screwed up there? Not an up arrow.
Yes.
It's the And it's because you get these temporaries that are built in the back. And for those of you who are lucky enough to have had a compiler course, even when you're just doing single, operations, you'll remember that the compiler is in registers is creating all of these temporaries. It's no different. It's just instead of a temporary floating point number, you have a temporary million floating point numbers or gigabytes. So
Yeah.
it's something to keep in mind when doing it.
Exactly. So.
It's huge. Your base type, like a float, is actually a couple of gigabytes worth of floats. It's fast, but you're also moving a lot of stuff.
And then, as Gordon said, it's fast, but we'll see that's not like super optimized. The fact that you have to do a multiplication, keep a temporary, and do a subtraction, and keep a temporary delete, that's not super optimal code. And we'll see in a bit how we can make this optimal, how we can optimize this thing. But this is, keep in mind that this is what the computer is doing when you actually do this compact formula, right? And then we'll see a little bit now. Yeah, let's do some timing stuff. So let me run these cells, and hopefully the result will come. So what we are doing in this first cell, here we are doing the non-array programming version, right? We explicitly write a for loop, and then we give in this quadratic formula actually each element of the arrays, right? We loop over the arrays, we take an element, we calculate quadratic formula, we put the result to this imperative, right? That's the imperative paradigm. So, yeah, it came up. So you see that's slow, right? You see that it's slow, you see how much it takes a loop. So let's see if this will come up. Yeah, it's coming. So when I take the quadratic formula and I directly operate and I put the arrays, I get like a huge performance difference. And this is because I don't have to write for loop. And for loops in Python are expensive. And this is what the powerful of array programming is. Instead of writing a for loop over billions of numbers, I can give these billions of numbers in the formula, and I can get a performance increase. And you will see that this, as I said, either if I give the pedantic, or if I give the quadratic, the compact one, or if I give the pedantic one, I get very, very similar. Like, 14 and 20 milliseconds, it's the same thing, more or less. So the computer, even if I give the compact one, NumPy is breaking down to this pedantic, and that's the best it can do. But we want to show you that sometimes you can even do better. And there are some libraries that, let me run these cells. OK, this is just. So there are some libraries that can help you actually fuse these pedantic sort of things that NumPy is doing. And by fusing them, you get even more performance. So there is this NumExpress, I don't know how it's called, library that's actually a sort of what's called virtual machine. I don't know if this term is very useful to you, but this is used a lot in sort of Pandas data frame. So have you guys used ever Pandas? Maybe some of you, yeah. Sometimes you write in code some formula, and then you go and you execute it in the whole data frame. This is what is run behind the scenes. Or you can do some stuff which I think to me it's more kind of useful. You can take this quadratic formula and you can compile it and either with NumPy or with JAX. So you can import this library called NumPy, and you can give this sort of how it's called. How this stuff is called in Python, like at something, how you call this thing? A decorator. You call it a decorator.
Yeah, yes.
Yeah, you can give this decorator. So what is doing this is compiling this, and is vectorizing it actually. So it allows you, it fuses these operations, and also allows you to use the hardware a bit better. because eventually what you're going to do, you're going to send this data to the CPU, and then the CPU needs to do these calculations. So modern CPUs can do multiple calculations at the same time step. So when you vectorize something, you actually start using the hardware a bit more, a bit better. You have a question? Let's see.
So when you vectorize using either or, are you still doing this temporary deletion, or like a temporary creation, deletion, temporary creation, deletion, moving things around like that, or is it?
So it's definitely more fused. Let me go to the. So the question was like, if I vectorize, if I keep having these temporary variables, right? So it's definitely more fused operation, and a lot of these things are not existing. I don't know, I cannot tell you if no temporary variable is used. Maybe it's used, I'm not so sure about that. But the operations are way more fused, and the computer has to do fewer things. It reads the whole program, and it knows about the flow, and can optimize of how to do it better, instead of doing it kind of this pedantic NumPy line by line.
One good way to think about it, kind of what you were just saying, is NumPy is eager. And that is, the second it sees A plus B, it has to evaluate. And it doesn't consider the fact that actually you don't really care about A plus B. What you really care about is A plus B plus 5.
Yeah.
Because NumPy just hasn't gotten to the rest of that expression when it's in Python. But these guys, as he's saying, the compiler or the backend gets to look at the whole expression and can now optimize and say, well, let's just do A plus B and just add on 5 for each element, eliminating some of the temporaries.
JAX,
You
yeah.
know, it's not perfect. It will use temporaries. That depends on the complexity of the expression. It's probably a way to know exactly how many temporaries it's going to use at a time, but I don't think any of us have
Yeah.
spent the time to figure out exactly what the rule is. It's much better than the eager evaluation that you see.
So, okay, can I go? Yeah, sure, no worries. No worries. So JAX is doing a very similar thing, Numba and JAX, but JAX is doing only array-oriented things. So, okay, in this expression, it's not too different actually, right? But here, when I use Numba, I can write an imperative program with 4 loops, with, I don't know, maybe sometimes if-else statements. When I write in JAX, I need to write something in a very array-oriented way to compile it. And I don't know. And in JAX, I can get even a better performance outcome, right? Although the expressions might be a little bit trickier to write. So that's the difference between Numba and JAX. That Numba is kind of compiling imperative code. JAX is compiling array-oriented program code. And I think we're going to get some, you're going to see a little bit this now. So in the first one, we have the NumPy version, where we feed an array, and you know, NumPy is doing this over all the elements of the array. As I said, NumPy is a little bit stupid. It doesn't know how to fuse the operation, and then you get these 16 milliseconds. But if you start using this more sophisticated like languages, this one with a virtual machine, you get even like down to 1 millisecond. And then, you know, Numba can, it's about the same order of magnitude in this example. And JAX, as I said, JAX can even drive you either to more performant code. But here it's different way these things are compiling. This is called just-in-time compilation. Maybe you have heard this concept, JIT. So in Python is an interpreted language. It doesn't do compiling stuff by itself. But then sometimes you can do a trick, which is called just-in-time compilation, and really go and compile a single line or few lines, right? You just compile a few lines, and then you can run this thing multiple times faster. So this is what NumPy and Jack is doing with a little bit different way. But the point is this, that we can even get better performance out of NumPy by compiling code, right? And then, you know, it's a little bit of history again of how compiled code can be. You will look at this later. There's no way you can look at this in this projector, and there is not so much sense. But it's a sort of how the technology evolved and how we were able these days to get compiled code into Python. And there is a lot of ways to get compiled code into Python. And NumPy is a sort of compiled code sometimes, right? Yeah. And again, NumPy has some great things. You can do element-wise operations with functions. As I said, this broadcasting where we can change types without caring too much, slicing, reshaping, and a lot of nice things. So that's an example. I think here we have a little thing for you now, right?
It says Quizlet, right? We put that. This is an example. So.
Right. So this is an example that I think you're going to do something as well. So what we want to do is compute the size of the spaces between consecutive elements. So I have an array here, right? Let's try to do some array operations. So I have an array with a lot of numbers. And what I want to do is figure out the size difference between these two numbers, between the consecutive numbers. So 1.1 with 1.2, what's the difference? 2.2 minus, yeah, with 3.3, what's the difference, and so on. So, yeah, I think here, what? Here we have the Slido thing, right? Yeah. So in your workbook, you should have a, what is called Slido thing there.
I think it's further down.
No, I don't think so.
Is that like the question and answer thing? I think I see one farther down.
Yeah. Okay. Let's.
I'm pretty sure it's further down.
Okay. Let's go further down. So what you can do here with a simple thing, you can use slicing of NumPy. And you can take a slice which starts from element 1. Element 1 is this guy, right? So I can take this array, right? And then, sorry. Yeah. So I can take this array, which disappears again, and then I can abstract this array, which starts, I can hear, which starts and goes, it starts from 0, you know, here you can put 0, and goes all the way to the second to last element. And if I abstract these variables, these two arrays, I'll get what I'm looking for. So this is a sort of array operation mixed with a little bit of slicing in Python, just to get you a little bit warmed up in terms of how it's going to be today, right? So you can do tricks like this and you know, figure out stuff about your data set quickly. And yeah, in a graphical representation of what we try to do is, you know, we have this array with the numbers, and then we took the minus of the other array, and if I do, you know, this minus this, I'll get equal 0, of course, element-wise. But what we did, we sifted a little bit, and that's why we got the difference between the two, right? So this is a nice trick that will be useful for today's exercises and projects and so on. Yeah, so that's a Quizlet. So that's maybe now that you can touch your computer yourself. So what I want to do is to compute the length of arrays x and y. I can make a linspace. It doesn't matter so much what you're gonna get here. And then for x, I will get the sinus of something. For y, I'll get the sinus of something. And then if I plot this thing, I'll get something like this. That's the curve. And what I want to do is get out the length of this curve. And how you get the length, you do delta x squared plus delta y squared, and you get the square root of this, of, again, consecutive elements. So you can try to code this a little bit yourself. That's the quiz thing. So we have this Slido here thing now that you can click to start, and then when you're done, you can click again and try. Yeah, give a try on this exercise a little bit, and then we can see the result together. And then I have the result of the Slido here, so I can track a little bit what you are guys doing and if you're done or if you have started and so on. Let's get 5 minutes of this.
So go ahead and put back the
I think you guys have the problem in your...
we do, but let's put it up.
That's the problem. Yeah. So again, I'll have 2 arrays, x and y, that if I put them together in this scatter, they will make a 2D line. And then I want to figure out the length of this line. And the formula to do this thing is this one.
Feel free to just, put your hand up if you have a question, trying to work this out. Happy to help us as best we can.
Ah.
You, excuse me, as best we can.
Yeah, this was supposed to take 30 minutes, and now it's already 15 minutes late.
I guess we're not going to have trouble.
Okay, we can reduce the 45 minutes breaks that we have. Let's see, okay. Some people are done. Some people are working on this. I'll give maybe another 1 or 2 minutes. Remember this trick that we showed before of how to calculate distance, like differences between arrays? Between elements of arrays. Well,
That cheat sheet, that NumPy cheat sheet that Vangelis showed earlier, just go to Google and type in NumPy cheat sheet.
okay, I see, Bob, all of us said that your guys are done, so I'm glad to see this thing. Let's see what is a solution. Solution is simple, right? What you had to do is calculate, as we said, delta x, delta y, square them, and take square root of this, and then take the sum. And how you calculate this delta x, this is how we saw before. This is a little slicing trick to calculate the difference between consecutive elements of an array. And then if you square it, and then you do the same for the y, and you take the square root, you take the sum, then you're going to get the result. Is this what you guys figured it out, right? How this problem was? That was, you felt easy? If you felt that was easy, we can do very well today, because that's a basic trick that you can use all the way till the end. Like, keep this in mind. That's a very good trick. I'll give a last thing. I'll do this quickly because we are late, and this is not very important to understand. It's just to show you some things of what NumPy else can do. So there is this endian thing. Maybe some people have heard this before, endian. What is this endian? I didn't know before. I learned for this class, I have to admit. So endianness, endian, of course, endianness is the way computers store the data, right? So you get a number, a float. You get a float. And this float, it's stored as a byte string, usually with, I don't know, some length. And then, you know, then the computer needs to know what's the significant digit, right? Is the first one of the byte string or is the last one of byte string? So you can take one number and then have the byte string, or either put it like this in memory or put it like this in memory. And modern computers do what we call little endian, right? So all the modern technology is doing little endian. So it starts, when you store the number in the memory, it starts with the less significant digit. But what we can do, we can take an array, and we can say that that's a float of 8 bit, yeah? And then if we put the symbol, we'll switch the endianness, right? So this array is stored with the wrong, to the modern standards, endianness, with a big endian, and you will see here that if I view this array, again as floats, I'll get random numbers, right? This is not a nice thing anymore, because the computer now is confused of how this is stored in memory. And then what we're going to do now with NumPy is try to flip the endianness a little bit by hand. It's a bit, you know, nerdy example, but you can see how you can change this thing. So I can get the raw bytes. I can see a little bit. If I give this array and do this view as unsigned integer of 8-bit, I can get the raw bytes, and that will be an array which is 8 times bigger than this, right? And you will see this thing. That's an array which is 8 times bigger, because every of this number is represented as 8 kind of raw numbers in the memory. Then what I can do, I execute this cell. I can group a little bit this array in 8s. So you see now that that's the representation of every single float in memory. As I said, every float is stored as 8 numbers, and that's actually a wrong wrong order. That's a wrong order, because we stored it as a big endian. So what I want to do, I want to flip this order. And if I want to flip this order, I'll fix it up. So we'll use sort of some tricks of slicing tricks. So on the first dimension, which first dimension are the lines. So in the lines, I'm not going to do anything. I'm not going to move anything on the lines. But what I want to do, I'll use this operator here to flip the columns. So with this guy, I can take this group. I can keep the lines same, but with this, I can flip the columns. So now, it's actually, each of these is reversed. And that's the correct thing. That's the correct endianness at the end of the day, right? If I will flatten this up again, and then, you know, I can show you that this kind of worked. So as I said, this example is not very important to understand, but it's maybe important to see what tricks you can do with slicing and reversing and stuff like this that you might be useful later. And I think now it's time. Yeah, let's skip. That's not very important. We skipped this last year as well. So I can get an example how to downsample a curve. So I have I have this sort of noisy data, which maybe we can represent as well. And then I want to downsample this noisy data. That's an important figure to understand, to keep in mind as well for later. If I have a sort of an array, how I can do reduction operations. So when I do a sum, a lot of times you can give this axis argument to the sum, to the NumPy sum, and this will tell you if you're gonna sum. This will tell you if you're gonna sum. If you put axis 0, you're gonna sum over the rows, while if you put axis 1, you can sum over the columns, right? And you know, if you plot this noise data, you're gonna get something like this, and then the quiz tells you to denoise this. So essentially, take the mean of every 10 numbers and replace it with the mean or the sum. This is going to be another slide, but I will skip and I will show you the result because we can save some time and it's not so important. So what I'm going to do is, let's say, take this noisy data and then group it in sort of in a two-dimensional array. Its line is going to have 10 elements, and then I can reduce every 10 elements and downsample this array. Yeah, and then I get the result. So maybe it would be nice to have a graphical representation, but what has happened here, it's similar to before, right? What I showed you again, I get the data, and then I make it in a more of a grouped. I group them in groups of 10, and then I can reduce in every 10 of them, and I get this sort of downsample curve. So again, that's an operation. That's the point of this, is to see how you can play a little bit with the shapes of arrays and do some reductions over axes. And I think that was the last one almost of our, yeah, now we can go to project 1. Now for project 1, you take your time, you can open the notebook, read through, have some time to, you know, yeah, I think we put 20 minutes there. You can get some time to have a look and.
Give everybody like a 5-minute break. Just
Yeah, you want to?
start the project immediately if you want.
Yeah, if you want. Yeah, you can take. We did already 1 hour on this to the intro. So you can take a short break, and then the project, we keep like 20 minutes for the project. So let's say at 3, we can start looking the project together and the solution, right? You have 30 minutes, take some break, and
Let me see if I can turn off this Grammarly thing.
which?
These crazy icons that keep popping up. They help me because I can't spell for shit.
Can it be a bit faster than my other one?
Yeah, the next one will be faster.
Yeah, there is no.
Okay.
this has as well 3 sort of solutions. We can do like 2 of those are enough, and this third just to show. The final one has a lot of options, but
At that point, we'll know when the end time is coming.
Yeah.
So,
so until what time we have here?
sorry. How much time we have right now? It's 2:45.
It's until 4:30. No, it's 4 hours.
Yeah, it's 4
So
hours.
it's like
till
5:30.
5:30.
Okay.
5:30. And then 5:30 is the reception.
No, I think it's tomorrow. Yeah, that's Tuesday.
Was that Tuesday? Oh, you're right. My bad. Yeah, so this goes all the way till 7 a.m. tomorrow.
We can keep here. It's fine. I'll buy the drinks.
Okay, so yeah, 5:30. So we're only just beyond 1 hour now.
5 more minutes?
We may need to give people a little more time. Or maybe what we can do is, yeah, so this was, when I was working on the solution for this, this was like really hard for me to remember exactly how to do the slicing. So what I found really helped was to create a temporary, just to play with small array, just like, I think I started with 3 by 3, because then I could easily visualize it. Like, so when you're trying to visualize that, it's just too much. Right? And then I wrote like a little method I could just run it and then play with it, and it was very fast. And I could see it in my head. I could do both dimensions. Like 1D was too easy. Because we'd done it, earlier.
I don't know. I'm lost. Okay, how can we go to solve this?
How can we go to which?
To solve
Oh, the solutions.
So it's
Yeah, yeah,
30
yeah.
minutes past. Why, do you have a question?
So how do you, is there anybody who finishes? I did not even expect, to be honest. It's a difficult problem. I don't think I would also solve it in like 30 minutes. I have done this problem before in myself, but the first time I don't think I would do it like 30 minutes. So yeah, don't worry about that. And what we can do is a little bit walk through together through the solutions and see how you thought. See how it's nice to think about this problem in an array-oriented way, and so on. So, yeah, I'll go through this, and yeah, maybe we can do it a little bit together. So this is about the how's it called, the game of life, right? It's a board that starts with an initial state, and then you put specific sort of rules that you update this board based on these rules. And these rules have to do with the neighbors of each cell. So each cell makes it to the next round, to the next step, if some conditions about its neighbors fulfilled or not. So we have these cells here that actually execute and make this new world with these dimensions and so on. So you can print it. Now it's going to look like a bit bad, but because of our zoom here. But that's, let's say, the initial state of this game, of this world, where it has this @ symbol. It's sort of 1. It's a visualization, right? Where it has dot, it's 0, right? That's so x, y are the dimensions here, and I give value equal 1 to some specific cells, and this is how I start. Make sense? Makes sense. So a solution to an easy solution is to use this NumPy roll, right? But wait, so
This trick I was talking about.
so.
If you know the trick.
You don't need to know this thing. So when I was going through the solutions, I didn't like that we start with the easy part. I mean, you can solve this thing without NumPy roll, and I will show you how to solve it without NumPy roll. But maybe this concept of NumPy roll, it will make you easy understand in your brain what is happening in terms of, education, not so much solution-like. So I can get an array which is going to look like this, let's say, and what NumPy roll is doing. So what NumPy roll is doing, it's taking this array and shifting it one step to the left, shifting it one step to the right, shifting it a bit up, and shifting it a bit down. So this is what NumPy roll can do in an array. You can shift these elements as you want. And also NumPy roll is a bit smart, so it knows about boundary conditions. So when this number is going to go here, then it's going to go here, then it's going to appear here. NumPy roll has this kind of built-in feature. So you can shift around and not miss cells. And this is, what you can do with this. You can shift it a little bit, minus one step, because when we get closer to the axis is -1. And this is axis 1. Axis 1 is the columns. So you see I don't do anything on the rows, or rows stay the same. I do an operation on the columns changing. And all the columns are shifted to the left. And this is what the other things can shift to the right. I can shift up. Now I do an operation over the rows. That's why I have 0. Columns stay the same, but I do an operation over the rows. That's very inconvenient to have this mic here. And then, as I said, NumPy roll wraps around the edges. If I shift a little too much up, then I'll get things appearing on the bottom. And this is useful
because essentially this is what the game of life solution is based on. You want to look at the neighbors. So for each cell, you can look at the neighbors by shifting up, or shifting down, or shifting to the left, shifting to the right. And if I keep adding what I'm finding to this cell after these shifts, essentially on the cell I will have the sum of the neighbors, right? That's the whole solution based on, even with roll or without roll. I have an array, I have a cell, I can move it a little bit up and down, and that's why I can sum over the neighbors. That's the basic concept of solving this problem. So, we can solve this in a 1D example to make it easier. Let's say we have this 1D array, and then let's say on index 1. If I shift this array to the right, this element is going to come here. You see my cursor, right? If I shift this array to the left, this element is going to come here. And then I can sum, right? And then if I sum, I essentially have the number of neighbors of the index 1 here. You see, what are the sum of the neighbors? It's 0 plus 1. Here it's like 0 plus 1, and total neighbors is 1. So yeah, that's the sum, the left neighbors. I can calculate the right neighbors, and then I can calculate the sum, and that's the sum. So if I do it in a two-dimensional way, the rolling, it's a little bit more complicated. I need to do 2 rolls, 1 roll per dimension, right, to find the neighbors. Maybe the simplest thing is to understand this line. I don't know. Right? This is in order to add the west neighbor. So in order to add the west neighbor here, what I'm going to do, I'm going to first do a roll of the world over axis 0. Axis 0 are the rows. Step 0, I don't want to move this thing, but I'll do a roll over the axis 1, and I do 1 step, and that's how I get actual moving the column and get the west to the center. And if you see, to get the northeast, for example, I need to do 2. I actually need to do 2 rolls here. You see both rolls have step 1 and -1. I get this element, and I shift it to come to the center. This is what the roll is doing. It's moving this sort of thing a little bit 1 step around. And then if I add up all of these things, then I'll have in its center, I start with 0, right? I start with 0, and I do all these rollings, and I add up. I keep adding up, and then in its cell, I'll have now a decision to make. And we give this to the hint. We gave this to the hint of the project, that I need to count the survivors, which of these alive cells make it to the next, and which are the new births, and return births or survivors, right? I want both of these to return. And this is the rules of the game. If the neighbors are greater than 1 or less than 2, it's a survivor. Or if the cell was dead and then it has number of neighbors equals 3, then it's a birth, and then I get my result. And then I can see a little bit step by step how this evolves. You see, this is evolving step by step. Does this make sense? The solution, what I did here, does it make sense to you?
So in place of the roll, you could also have, not had your world wrap around at the edges, not make it closed world, and just done those offsets with
Yeah, this is
similar to what we were doing before.
what we're gonna show now.
Yeah, but I'm just saying.
Yeah. But I think that all it's maybe useful to understand where we're going. That cell in the middle, I can roll the array around, so I keep summing up the neighbors. Right. And now, okay.
So does that algorithm make sense? I mean, thinking about it from the array point of view, is that? I mean, it's really different from a single, taking a single cell and then looking at the cells around that cell. Instead, you're sliding the whole world around in order to determine totals. You have your hand up.
Sorry, earlier you were explaining the east-west lines, where you roll but at shift 0.
Yeah, because in order to get the east, I don't need to shift in 2 dimensions. I just need to shift in 1 dimension.
The 0 is there to keep everything aligned, so it looks pretty when you're looking at it. But it's a no-op.
Yeah.
The NP roll world 0, whatever.
Step 0 is doing nothing.
It's doing nothing. It's just to make make it readable.
Makes sense. All right, so how would you solve this problem? Okay, you can time it, whatever. I don't think we care too much about this right now. So how you solve this problem without knowing NP roll, right? With what we said today, right? About slicing and stuff like this. And to be honest, I didn't expect you to know, I don't think people should be expected to know NP roll. But we already gave some hints of what was happening, how we can find differences between elements, how we can sift an array actually by 1, and so on. So we gave these hints on the first part, and this is what we're going to do today, what we're going to do now. So you have this array, right? Again, 0, 0, 1, 0, blah, blah, blah. So how I can get the left neighbors, right? The left neighbors of index 1, right? It's like slicing this array and taking these elements, right? If I take these elements, then I have the left neighbors of its index.
I think you wanted everything but the last one, not skipping the first.
Yeah, but look at this. No, you need to skip the first because the question mark.
Nobody goes 0, 0, 1, 0. You have 0, 1, 0, 1.
Yes, you're right. You're right.
It's
Yeah,
really
yeah, you're right. You're right. You're right. I'll take exactly. You take everything. Yeah, you're right. You take everything except of the first one and make a new array. And these are the left neighbors of your initial array. Of course, you don't know the left neighbor of this guy, right? That's why we have a question mark here. And what I'm going to do to get the right neighbors of every element, I'm going to do the other way around. I'm going to skip the first element and take the rest one. Well, it's mind-blowing. In this way, I cannot know the right neighbor of index 6, but that's fine. Let's keep it as a question mark right now. Right? And what I can do, I can sum these two arrays, and that's how I can get the total neighbors without actually knowing the boundaries, what's going on the boundaries. But that's fine. Let's forget about the boundaries at the moment. I think we showed you already this trick of how to slice an array in such a way. And before we subtracted, now we're going to add, right? It's this guy. So, you can start with zeros, and then to get the left or right neighbors, one you need to take from the first element till the end, or from the beginning till all, how's it called? The second to last element, and then add up, keep adding this together. And this is how you get left or right neighbors. On the boundaries, you have zeros because we started with zeros, and you don't know what's going on, but let's keep it like this for the moment, for simplicity. So this solution is correct without taking care of the boundaries. And then if you get this trick, then I think you're kind of done. You just need to code this. It might look a bit weird, but it's based on sort of same concept, that I'll get my neighbors by sifting, not sifting, but looking at the left neighbors, looking at the right neighbors, looking at neighbors on the top row, neighbors on the bottom row, and I can look at, I can do a two-dimensional also operation. So you see here, I put, I want to sift in both dimensions and so on, and I'm gonna keep adding to do this thing. What about this solution? Does it make sense to you? Did you understand what we just did? I think, it's important, I think, to get this one-dimensional of how to, and I think important for me to be able to understand this thing. To be able to scale it up to more dimensions, it's just a matter of, being comfortable to do this in more dimensions. It's not, if you spend some time to understand what's like line by line, it's fine. But the idea is to be able to use slicing in a smart way to understand that how I can, look at, consecutive elements. I'm giving some time, so, maybe you want to say something, you have a comment or a question, that's when.
It's annoying looking the 8 rows of shifts. That's why.
What,
like
this thing?
Yeah, I don't like having to handle each corner differently, like with a different line of code. It just.
You could almost certainly put pieces of that in a loop. I mean, you're right, you're going around. I think that would make, for the tutorial, it would make it much less readable.
Yeah, this doesn't look very pretty, I would say. But, it's the whole point that how I do operations over the whole array instead of writing a for loop that looks like element by element and counts the around elements, how I can do this collectively. So sometimes, you need to think a little bit in a different way of instead of element-wise or imperative programming.
One of the things is with science data, normally when using NumPy, we think of every row being independent. Often each row is like a measurement or something like that. So it's very rare that you would start to think, oh, I need to relate something that's going on row 3 with something that's going on row 2, except for maybe it's an aggregation, like a mean or a sum or something like that. As we get further into this tutorial, we'll start to have data that has structure, which means we start to need to think about things not just as single rows, but as larger blobs, I have a better word right now, of data. And part of what we're doing here in this part of the tutorial is trying to get people to break out of that single line is all you need to consider mindset. Is to start thinking a little bit more holistically about this data structure. It's not good just for each line being independent. We can actually do quite a bit more.
So I can, yeah, here you can see that the two steps agree, but okay. But then I can probably show you that this is working as well to propagate the world as their all function. As I said, this solution is actually neglecting the edge effects, because with this solution, we don't know what's going on around here. You have this question mark. So if you sift the array, you don't know what's the left neighbor of this guy, right? You just figure out the other guy. And then if I'm not going to go through the detail of this. You can solve this as well by keeping track, by padding the world, expanding the world for another round of cells. Let's say I have the world, and then I put another round of cells around the world. And then I do a little bit of bookkeeping here. So again, this solution will be wrong for the padded world, but it will be correct for the initial world inside. So for the initial world, you have solved the boundaries problem. For the padded world, you still don't know what's going on with the boundaries. But we don't need to go through. It doesn't give you some extra, to be honest, much knowledge. It's just a more complete solution for you to have as a reference of how to do this thing with the boundaries. And then we had also this sort of trick, the convolution, which is, if you know, this is what I was saying, that if you are familiar with the convolution operation, then that's a very easy problem. Because this is what convolution is doing, actually. You have a center, let's say a center cell, and then you can define a convolution kernel in such a way that if you apply on top of this, convolution is a sort of multiplication by element, right? So if I take this guy and I overlay it on top of here, and I do this convolution operation, which is a multiplication by element and then a summation, right? Then I'll get the number of neighbors, right? Maybe I have one. Let's say if everything is 0 and 1 is here, the total sum of this guy will be 1. So then for my cell, I'll have number 1. And that's a very easy way to count the neighbors with convolution operations. Are you familiar with this sort of operation in mathematics, convolution operation? I see a couple of people moving their heads. Other people, no idea.
So, this morning there was this NumPy class, and we were talking about this filter code going around cells, which was, I immediately thought of this as sort of an automated way to do that exercise.
And then you see that becomes like a single line solution, right? You can take the world, and you can apply this kernel, this convolver. You need to do some kind of argument here, which is called same. This will just return you the same shape of output as what you gave in. And you can tell it to wrap around the boundaries, and then it's just going to sum everything, and that's the number of neighbors. So this is going to return a new array of the same shape. In each element of this array is going to be the sum of its neighbors. And then for each element of this array, I can go and do this thing that we gave you on the hints. I can see if it is 1, then I will check this array, the number of neighbors, if they have greater than 1 or less than 4, and then the births, if it is 0 on the initial world, then the same criteria, and then I will get the logical OR between these two. So you can see that this is working as well. It's not working because I didn't run this cell. So this is working as well. So again, I'll summarize this. It's like 3, I'm kind of have 1 minute left. The basic idea was to be able to count the neighbors, and the very deep, like, basic thing on this was actually some sort of thing like this. You take the whole data structure, you move it a little bit around, and every time you sum what you see here. And this, you do this at the same time for all the elements. You can do this with NumPy roll, easy thing, or you can do this with slicing, just see what is next to each other. Right. I think that's the end of project 1. Any question? Something you want to express? Okay. So we have part 2 now, and we can give you some break. Now we had a 15 minutes break, but we took a break before as well, so we don't need to do a 15 minutes break. And part 2 has no exercise. It's just me showing you a limitation of array programming and how you can get a way of it. What, do you want to do a 5 minutes break just to stretch a little bit, maybe get some water or something? Yeah, I see some heads are moving. And then I can go to the second one. Yeah, and I think we can do a bigger break. We can do a bigger break after the part 2 before we get into the part 3, right? Yeah. Do you want to come and set it up?
Sorry.
Do you want to come and set up the part 2?
should be safe now.
Right. So we have 2 hours left, which I think is plenty, if I keep on time. So as I said, this part does not have an exercise. It's just demonstration of a limitation of array programming and how you can get away with it, some ideas. And then maybe we leave more time for part 3 that Gordon is going to do the talking. So if I take 30 minutes to do this thing, then we have an hour and a half for the final part, which is a lot, so we can do a 15 minutes break. And then we have 1 hour, 15 minutes, which is still fine. Okay, let's try to do this thing. Right, so now we'll talk a little bit about control flow. Right, so that's something, it's a topic I touched before, this single instruction multiple data, SIMD model. Has anyone heard about this thing before? SIMD model of processing? No? No, okay, I need to start very basic. So, computer has the CPU, right? That's the basic thing of a computer. It's the central processing unit. So in a very naive thinking, one number goes in, CPU is doing something, one number goes out, right? This is how CPUs used to work for a lot of years. And this is a time step for the CPU, right? It's one number goes in, computation, one number goes out. That's a single time step. So when you write your software, there are a lot of what is called the compiler, and then there is this low-level language. So all the software and all the logic is actually goes down to boiling down to zeros and ones, and then the CPU is just doing this sort of operations, taking numbers, doing a simple operation, taking a number out, and then this is the result, right? But what is important to keep here is that in a classic kind of CPU processing style, one number goes in, operation, one number goes out. And then for a lot of years, what people who were making hardware was doing is making the CPU faster, right? Making this cycle faster, like one number goes in, one number goes out. But let's make it faster, faster, right? But there are some basic principles and some also material science principles that does not allow you to go faster. There is a limit where you can go. Then you start hitting so much the CPU, and you have some other problems, and actually the material itself doesn't allow you to go further on how fast the CPU can work. So then they thought, we're going to do something else, right? We're going to make the CPU a bit wider. So instead of giving one number goes in, one number goes out, we can give, let's say, 4 numbers goes in, 4 numbers goes out in a single time step. So it's like taking the CPU and make it wider. And this is what vector registers are for the CPU. A register, it's a sort of memory, it's a very little memory, piece of memory before the CPU, where the input is stored and the output is stored. So if I make this register a bit wider, I can feed more numbers in, and then I'll take more numbers out in a single time step. That's important to keep in mind, in a single time step. And this is what this processing model, I don't know how to say, single instruction, multiple data. So you do a single instruction, a single time step, but you do it in multiple data. And this is very close to what we are talking about today in array programming, right? We do operations in a lot of numbers at the same time. So these concepts are very close together. It's not exactly the same because one, it's about hardware, the other is about high-level software, but it's very close concept in terms of, to think about. So I do an operation in multiple numbers at the same time. And GPUs, which is like very modern sort of hardware, they have like only this vector register, but it's huge. Like you have huge amount of numbers goes in, in a single time step, huge amount of numbers goes out. And that's the benefit of GPUs and other sort of vector processing units. Does this make sense? A little bit, yeah? I try to make it easy. So, you can do this sort of example of what I described now. You can code this up. That's a simulation. That's just a way to code up what I was just talking about. That's not really. So you can make this scalar register that it has one value, right? And then it has an addition operation. So when you take a scalar register and you add with another scalar register, what is happening is you take one value plus the other value, what I described. One number goes in, one number goes out. And then you can make this modern, let's say, vector register, where this vector register, it has like 4 values anymore. So when you make the addition operation, the output is actually over all of these 4 elements at the same time. You see this thing here. So I have 4 additions happen at the same time. That's a little bit the concept, and you can get some numbers. Okay, it says raw memory. You can say, let's say I store some numbers in the memory, and then I can make, I can split these in 2. I can take the first line and the second line, and then I can do a for loop and use my scalar register. Why this doesn't print? I don't know why it doesn't print. Gordon, do you know why it doesn't print? I would expect to print, no?
Why don't you just go out of, click on that.
Ah, it's still running something.
Why is it?
Maybe it just got stuck.
Yeah, restart the kernel. Now try running that guy. Okay. Huh. Well, demo gods looked at us really nicely for a little while. All right, let's restart there.
Just close it or you want.
Yeah. I don't see.
Sorry?
Well,
You know what? You know what?
What?
Let's shut down all the, because we
Yeah.
have some kernels, let's shut
Shut
down
them
all the
all.
kernels. Yeah, I might run out of
Yeah.
memory.
This has 64 gigs. I don't think I'll. Okay, let's try. Yeah, that wasn't it. That should have been instantaneous.
You don't have, just have one guy. One guy is fine, right?
It's had no problem at any other point today. May
Where's the...
I? Okay. Sorry, folks. Yeah, it's really, something is really,
We had some bad people working around.
it's got the right kernel.
So for you it's working, right?
Yeah, but they're totally,
What, you want to run it locally?
it has been running locally. What I am just going to do.
It's not the Barry.
No, because we don't get the slides there. So I am. Always, yeah. All right, so let's just restart.
Okay, as long as Gordon is doing this one, so, I like this possible, vectorized operations and CuPy.
Here, do you want a microphone so people can hear you?
Right. So yeah, with the code, what we'll try to do now is to emulate and simulate a little bit this thing. As I saw, we're gonna make two structures. One structure is just a scalar operation, adding 1 plus 1 numbers, while the other structure is a vector operation. So it's when you give it two vectors, it's just adding like 4 and 4 elements. And if I could translate this to a CPU, actually, then both of these addition operations would happen at the same time step. So you see that when with a vector, I have a sort of 4 times more performance, essentially, right? I get 4 times more results at the single time step. But this is not, of course, what's happening here. This is just an example, an emulation in code. Right, yeah. So what I did here, as I said, we make this, let's say, example of raw memory, something numbers. We split it in two. This left is the top row, right is the bottom row. And then what I can do a for loop. And then I can use my scalar registers in every step to get back the result, right? And you see, I add these numbers, but I need this for loop over 12 elements. Of course, that's a scalar thing. But if I use my vector register, I can do just 3 steps, because in every step, I add 4 numbers. So this for loop is kind of cheaper, right, essentially. Or you can think about this as a cheaper for loop, because it just needs 4 steps to give me back the same results. And now it's run like I get back a set of 4 numbers. Yeah, this is the same thing that it says there. It's, yeah, what I said. What, I need to do some...
No, I just realized I hadn't made it full screen, so you've got all this extra Chrome around it. So there, that looks a little better.
Let me run these cells to...
You can make it bigger. Is this big enough? I can't remember if this is the same size it was before.
Maybe it was a little bigger.
You want it a little bit bigger? I can make it a little bit bigger. Yeah. It's fine? Right. So the problem with this situation now is that I did these vectorized operations, these 4 elements, at the same time step. This is what I was talking about with this old CMD and this simulation. I did these 4 additions at the same time. The problem is that I cannot have good control of the flow here in a way that I'm always doing additions of these 4 numbers at the same time, and I cannot control, let's say, the addition of the 4 number based on the result of the 3rd number. I need to do this all at the same time. So if I had a for loop, I could do, okay, run number 1, addition, run number 2, if it is, bigger than this, or run the next one. If not, don't run the next one. So I have, with for loop, I have a control of these operations, but with when I do it in a vectorized way, in a CMD way, in an array programming way, I don't have control of these additions. Always it happens. And this is what essentially says here. I cannot control the 4th addition based on the result of the 3rd. And that's a little bit of a problem here. Yeah, and then we showed before in part 1 how you can compile the code and make it vectorized with NumPy. But sometimes you might get complaints by the compiler there. If you have statements that change the control of the program, like if statements or for statements, because then it doesn't know what to do, right? In a vectorized way, you have to do all the steps at the same time. And you cannot control 3 or 2 of these elements. You need to do it all at the same time. Does it make sense, right? So you can think like NumPy as what I'm describing all this way now, like the CMD. It's not exactly the same concepts, but you can think about this as a single Python instruction applied to multiple data. And with the same limitations here, essentially, what we're going to show here. And NumPy can be essentially compiled to do this actual hardware vectorization, to use these wide registers or not. But the point here is that with NumPy, we omit Python operations, right? We don't write for loops, and we do a lot of things in Python over a lot of elements with less operations. Even if it is compiled to use the wide registers or no, we save Python instructions, and that's a benefit you get essentially, right? That's a little bit complicated, and I don't want to go into too much detail if you are not interested. But you can think about NumPy as like a high-level CMD that I'm saving Python operations, no matter what happens on the hardware level. And now we're gonna show a little bit this limitation that you cannot control the flow of this, and you cannot control the operations into all the elements. You have to do it all together. So maybe here I missed some spaces. So let's say that I wanna use calculate a special function. That's the log of the gamma function, and this is how it's given, but then I can go to the book and find actually an algorithm written in the book that is calculating this thing, actually, the log of the gamma function. It doesn't matter to know exactly the details, but you open the book, and if you open the book, it's going to give you this function, right, in this page. So if you want to calculate the log of the gamma function in the point x, you need to write this. Sort of function. So you will see that there is. You don't need to know exactly the details. You will see that there is a for loop inside here, but this is still what we call a closed form expression. Because this for loop is essentially going over these elements. So instead of writing a for loop here, I can write just blocks of, this for loop is just taking this number and put it here and then keeps adding. And this is it's just like a small for loop of 6 numbers, and then you make an addition of 6 numbers. So you don't really need a for loop here. You can write this without a for loop. And then you can return this result. As I said, it doesn't make, it's not so important to understand the detail of this, but it's to understand that that's what we call a closed form expression. It has a definite answer, and we can actually compile this. We can do it very performant. We can apply to like millions of data very, very nicely. Let me run some things. And then I made some, wait, I want to show you. I wonder where I defined axes. I'm looking for, that's the definition, that's import, and where, it's here, okay. Yeah. So what I can do, I can define an array by linspace. I don't want the zeros, that's why I put it here. And then I can define another array, which is given by the log of gamma for x in XS. This is not array programming, right? This is a kind of for loop, but it doesn't matter for this example. And then I can plot, and I can get this. This is the log of gamma in every point, right? So this is essentially writing a for loop, taking every element from XS, put it inside of the log gamma, getting a y out, and then you plot it. Not array programming using a for loop. But I can do it in a array programming way, essentially, if I can just take the solution from SciPy, which this is exactly the same thing as we wrote explicitly before. The definition, we gave the function, but SciPy has this coded up already. So, and then I can feed the whole array inside and do this thing without a for loop, right? I can do it in a more SciPy way. And then same thing applies. This is what I saw. This is what I discussed on part 1. If I write a function in Python with NumPy, I can even use scalar values, do a for loop, pass a value, take a result out, take the next number, blah, blah, blah. Or I can pass a whole array out in, and I can get a whole array out. And this is what it happens now. You see, what I will plot here, I will calculate log of gamma, but this is an array programming way. I'll give the whole array here, and I'll get back a whole array of results without a for loop. So I can do stuff like this. I can define a function, and I can pass a whole array in, and I can get a whole array out. Right? As I said, this is allowed. You can either pass scalars, or you can even pass vectors, arrays. And this is possible that because this function is actually what I said, a closed form expression. It has a definite answer. So whatever number I give in, I'll get a definite answer out. Even if there is a for loop inside here, this is a small for loop. It's actually don't really need it. But the important thing here is to, to understand or know that whatever number I pass in, I'll get a number out. That's, there's no way to get screwed here. But this is not always the case. And if you look to another function, which is what is called incomplete gamma, right? It has this expression. Then you go again to the book of how to calculate this this incomplete gamma for points A and X. And then the book is tell you, you need to write this algorithm. But this algorithm, it has a something which is tricky. It has this if statement here. So the book will tell you, okay, calculate this GLN, calculate this delta, and then for loop at about 100, right? And then keep track of delta and summation. And then in each loop, in each element, you need to make ask yourself something. Ask yourself if this absolute delta is less than this guy. So if it is less than this guy, then you will return, and then you converge. Maybe you converge in for loop number 5 iteration, maybe you converge in 50, maybe you converge in 99, or maybe you did not converge. So this is not a closed form expression anymore, right? Because depending on the numbers I will put in, I might converge in a different state, or I might not even converge at some point. And this is where problem starts with array programming, because the behavior of the output really depends on the input. It might be not, might be something else. So let's give this example a go. So again, I will make a linspace, and then I'll do this in a sort of a classic non-array oriented way. I'll take my incomplete gamma, I'll put some values of alpha here, and then I'll put various values of x's, and then what I'm gonna get back is these curves, right? And then it's working. This is a for loop actually, right? It's a bit hidden, but it's a for loop and it's working. And then, again, I can do this with SciPy instead of doing this on my hand-defined function. fine, I can give an array. But what has happened now, if I give in this incomplete gamma with alpha value 0.3, this whole XS, this is an array of length, I don't know, whatever, 1,000,000. So this is not going to work. This is not going to work because the behavior of my incomplete gamma depends on each value of this XS. And if I go back, what is going to happen now? You're going to get this error that the truth value of an array with more than one element is ambiguous. So what does this actually means is that, you know, this is a problematic statement because I gave it now an array of length 1,000,000. And I'm asking it to do it array programming way, do the same thing in an array of 1,000,000. But the problem is that depending on the value of each element of this array, the algorithm might converge in a different place, or the algorithm might not even converge at all. So that's not something I can easily do in array programming. When I have these non-closed form expressions that might return at some point, might not even return at all, might raise an value, or yeah, when I have these if-else statements, I cannot. So what the error says that, you know, delta is going to be an array of 1,000,000, right? I'll give x is an array of 1,000,000, and delta, because it has x, is going to be, let's say, an array of 1,000,000, and p absolute delta is going to be an array of 1,000,000, and summation as well. But then when you want to see the if of this expression, this is going to be an array, again, let's say, of the length of 1,000,000, but with different decisions in its element. Some decisions will be true, some false. So that's why it says it's ambiguous, because it tries to make it kind of one thing, but it doesn't know how to make it one thing, because in its element, you took a different decision. And that's the problem. And yeah, let's see how to go further. Yeah, this is what it says here. The Python cannot decide whether to enter the body of the if statement because the expression might be true for some elements or might be false for other elements, and it doesn't know what to do. So there are a couple of ways to get around of this. The easy thing is to just keep going, right? I'll do my for loop until 100, and then I'll calculate these numbers and I'll return this thing. I'm not going to put a return inside any if statement or something. And this is actually burning a little bit of CPU, or you do redundant calculations, because some of these evaluations doesn't need to reach 100, might converge at like 5 or might converge at 10, but to make things simpler, I'll just let all of them go to the 100, and I'll get the result at the 100th step, right? And this is going to be fine, and this is going to work. That's a closed form expression, and you know we can make it work. Or you can do the other thing, which is a bit more tricky, is to do a sort of bookkeeping and essentially make a new array and put it in a way in order to calculate these steps when it's not converged. And you know, you can see a little bit. It's a bit more complicated expression, and I will show you in a bit that this is not even needed most of the times. You don't want to do this thing. So you can actually tell it, calculate this delta summation and not converge, blah, blah, blah. Calculate it only for some values and not the whole array. That this is what the parentheses, the brackets show here. And then that's not converged. It's like a logical sort of operation, right? That's going to be an array which stores logical booleans, yes, converge, no, it didn't converge. It's a bit more tricky, this thing, and what I want to show you from this is that you can write it, but it's not maybe the best idea to write this thing, because here you pay some performance, you pay a price of extra operations, and you will see now if I do the, okay, this, you will see, this is gonna work, okay. Yeah, I want you to see these two things. So I have the function which is keep going until 100, and then I have the tricky bookkeeping function, right? And then I'm gonna time these two things. So you will see that hopefully, let's see the result of the second, you will see that this is actually faster. And that's a nice thing to keep in mind. Even if I keep doing operations, at the end of the day, it might be cheaper to keep doing operations than introduce complexity into my function. So a lot of times we do this thing in our applications. We write the simple thing that might do a little bit more extra steps, but it saves time because it's doing less of careful bookkeeping and careful Python and memory management and stuff like this. So, you know, I show you this tricky bookkeeping, but I'll tell you that, you know, probably just let it go, and you'll get the performance out. And I think that was almost the end of this. Yeah, start project 2, but we don't have a project 2. Yeah, what do you have any questions or something on this? I think that was the end to show you a limitation of this array programming thing. Yeah, okay. Keep this in mind. You can have these closed form expressions that you can definitely get an answer. You can feed it to millions of data in an array programming way. But if you have a non-closed form expression that the outcome is not, it has a little bit more logic inside, then it's tricky to apply to an array programming way. And you need to think workarounds. That's the point of here, that array programming works, but it's not whatever I write, I can scale it out with array programming. Good. I think yeah, now we can stop here. So now it's 4 and 5 minutes. We have 1 hour, 25 minutes till the end. What do you?
What if we resumed at 4:15?
4:15. Yeah, we do a little break.
Just under, I mean, it's short, but enough time to get up and stretch legs or grab a snack or a lemonade. I don't know if you made it all the way to the side, but they have snacks out, to, at least they did last time before I assume there's stuff. You want to grab some. So come back in about a little less than 10 minutes. And we'll do the last piece. No idea what I think, huh?
What?
I have no idea. I really just had to tear it all down and put it back together again. Say again? Okay. Okay, in the interest of making sure that we finish on time, let's get started. So we're going to continue down the same paths that we've been up to now, but we're going to add a slight twist. So instead of these gorgeous, beautiful NumPy arrays, which are all even at the edges, every row has 50 columns, or if you have a third dimension, each dimension is exactly the same. Each is exactly the same same length as every other piece of that dimension. We're going to look at array-like data structures which follow NumPy-like semantics, but are a little bit more complicated and have some big benefits, especially when it comes to storage efficiency and other things like that. All right, so NumPy arrays are all rectilinear. That is, as I just said, they've all got nice, neat edges. So, okay, that second huge Rubik's Cube isn't quite all aligned, but you get the idea. Every dimension has, if one column or row in one dimension has a length of 10, then everything in that dimension has a length of 10. And we call this rectilinear mostly. But what if the data looked a little different? Like this, for example. So you'll notice here we have array that's 2 long in here. Then we've got one that's 3 long, but it's actually 2, and the second one is 4th, right? Where this is only 1 entry. Down here, we've got empties. Here, we've got nothing. So in short, we are now in a situation where the data is kind of a mess. I mean, it's still multidimensional, right? This is a list representation of a potentially a NumPy array. I mean, to represent this in NumPy, we'd have to do some padding, right? Like, let's see. I think 2 is the most that we have here. Nope, we have 3 on this line. So we'd have to here add 2 more lists. For this one, we'd have to add 1 list, this one 1 list, this one 1 list. Oh, this one has 3 here, and here we'd have to add 3. But then we'd have to pad each one. So for example, this guy has 1, 2, 3, 4. So we'd now have to, this dimension would also have to have 4. So 1, 2, and then we'd have to somehow like none or something like that in order to represent and bring it out to look exactly like a rectilinear data structure, for example, like NumPy. However, that you can imagine would be incredibly expensive. Like think of a, just something 10 by 10 by 10. So a 3-dimensional NumPy array, 10 times 10 times 10. So that's what, 1,000? Okay. 1,000's not big. We can do that, but it quickly gets out of hand as those dimensions increase in size. But what if the 10 by 10 by 10, but almost everything you've only got like 6 or 7 things in each of these sub rows, and it's just 1 or 2 of them have 10. So this means a tremendous amount of wasted space. Okay. Oh, here's another example. Okay, this one I kind of like because now you can start to see some structure. So here we have a fill at kind of the top level. So fill, fill, fill. And then underneath fill, we have okay, where's the points? Oh, here's points. Right, so here we have points, and we have a list of points for the fill. Here, for example, we have many more points inside the list, right? Here we've just got 4. Here we had 2, 4, 6, 8, 10, 11. So you can already see this as sort of how the data structure is being built up. We have an array of fills, and for each fill, amongst other data like I guess the color number and the stroke, etc., we have a list of points which probably describes some sort of a closed
closed polygon, which we're then going to fill with that color. So we have kind of a hierarchical data set that we're building up. Still very much in an array format, or you can represent it, obviously, in an array format. Okay. Here's another one which we'll be working with a little bit later on. A list of movies. And then for each movie, we have sort of a single scalar, the year, and then a list, which are the actors. Differing numbers of actors in each for each movie, but always a single year and always a single name. Okay, fantastic. So, it would be very nice to be able to use all of these tools, like from NumPy and the high-speed tools, to be able to process this. Maybe it's not as fast to process strings as it is to process numbers, but one can think of that very first example I gave where it was all numbers, if you wish. All right. So we want to turn these into this tabular form and use, we could do this by, for those of you who have had some database background, there's this process called normalization, which effectively flattens everything into connected 2D tables. So we could represent all of that information as a series of NumPy arrays as opposed to a single NumPy array. This is much less efficient depending upon what we want to do, but it's starting to get ugly and inconvenient. Getting to that point, especially cleaning up the data, is quite difficult when you're in this sort of normalized, form from database theory. In fact, people who do databases have invented all these tools to sort of reconstruct the hierarchical form so that they can look at their data, although it's all represented in this flat, normalized, individual, multiple table form. So maybe instead of trying to do that, what we can do is keep it in the natural form, this hierarchical array form. Okay. Sorry, I basically said that. So we want arbitrary data structures with array-oriented interface, but really important, frankly, is the array-oriented performance. We're doing, the science problems we're tackling have huge data sets. We want to be able to process them efficiently. We want these huge advantages that NumPy has been able to give us, the expressiveness and the speed, and we want to be able to use that in this data that looks much more hierarchical than it does like a straight spreadsheet. Okay, this is a well-traveled area in the Python scientific and data processing ecosystem, and there are a couple of key players here. Arrow, something called awkward array, and Parquet. My guess is people have probably heard of, how many people have heard of Arrow? Okay, how about Parquet? Okay, more hands there. All right, perfect. So Arrow, it's an in-memory format and ecosystem of tools. When you go read it up, they have this tagline. It's exploded database. I don't actually know what that means, but it's words that they use all the time to describe it. But the key thing is there's a strong focus on delivering data, zero copy, and you're doing that between processes. So if you have to ship around data, be it NumPy-like data or this more messy data that we're going to talk, that I'll give a nice name in a moment, Arrow is a big friend. In fact, the layout for Arrow has become kind of a standard in-memory format, which lots of different libraries now use and interface with. So it's one of these great things about the Python ecosystem. We've chosen a memory layout and a basic API, and now everybody can bring something to the party and add things on sort of self-reinforcing both the efficiency, convenience, and of course the ecosystem. Awkward Array is the library that we'll be using a little bit now for the rest of this lecture. So it's a library for array-oriented programming, so using NumPy idioms, but arbitrary data structures. And it's zero copy convertible from Arrow and Parquet. Zero copy may not, basically zero copy means that the memory layout is identical. That may not sound like a big deal, but when you have gigabytes worth of data in memory and you need to move it around, zero copy can make minutes worth of difference depending upon the memory architectures that you're dealing with. Okay, so the arrays that we're talking about are these arbitrary data structures. We sometimes called them jagged arrays, but awkward arrays was the name we gave the library. And so this grew out of this is a major issue for us in particle physics, where this library grew out of, although it's now used outside, by quite a bit outside of physics. Finally, there's Parquet, which is a disk format for storing these large data sets and retrieving them. And the beauty is all of this works together. Yes?
How does this relate to like PyData.sparse or SciPy, like the sparse array?
Okay, so how does this relate to the other sparse array libraries that are out there, like PyData.sparse and the SciPy one.sparse I wasn't aware of? I'm sure there is, but right.
Two of them and one is supposed to supersede the other.
Ah, okay. Okay, so so one is age, but the other one was that, at least when I last looked at it, this had been tuned to really just copy NumPy, and I had not thought that that was the case in the SciData, the SciPy one. But I have to go back and look. I haven't looked at those in a while. But the beauty is because we have Arrow as kind of the in-memory data format, all these other libraries, like if you needed to write a new operation, you wouldn't necessarily have to use the awkward array kernels. You could use kernels from someone else, and it would interoperate now with awkward array, because everybody has decided that this is the standard in the Python data ecosystem. Okay. Whoops, sorry. All right, so sorry. All right, so as an example, with PyArrow, you can create an array exactly in a very similar way that you would NumPy array, but since it's an arbitrary data structure, we need to start giving columns names, or we need to start talking about structure. So one of the ways to do this is with a dictionary. So you'll notice that the array starts out as a list. So this is like NumPy. We often talk about rows, right? So here is one row, here's the second row, and here's the third row. I'm trying to count. Sorry, I'm trying to count brackets as I stand up here, just to make sure there isn't an error. Okay, so here, right, you have the X and the Y for each one of these. Notice the data types. X is always a floating point number, right? And then Y is always a list of integers. Okay? So now we can look at its type. So the type information should give us basically the information I just gave you. It should be a list of every arrow. So it should be a list of rows, and every row is a list of dictionaries of X, Y points, where the X's are floats and the Y's are integer lists. Okay, oh, you know what? This was already rerun. I forgot to clear all the cells from when I tested this. Now you guys get to see everything up front. Okay, so you'll see there list item with a struct. X is a double, and Y is a list of integers. Okay, I don't like that you guys can see the future here. Where is it? Is it clear? Where's clear all cells? Okay, there we go. All right. Now you can't see anything. Oh, did I just scroll up? Oh, yeah, you're right. Thank you. Okay, so let's get the array type back. All right, and then we can look at the a complete dump. Sorry, a complete dump of the array. So now we have a list of everything there. So you can see the x and the y values. Notice that we've lost the column names here. However, all the data is back in there. Personally, I do not consider this to be a very readable representation, but it's PyArrow's default representation. Okay, so that is this sort of this agreed upon in-memory format. Now, awkward array uses that in-memory format for doing many of its calculations, and it really, what it's trying to bring to the table are the NumPy expressiveness and semantics. And in many cases, it tries to keep what you learn for NumPy will work for awkward. So here, we can just load, we can just take the array, 0 copy, load it to be an awkward array. Ugh, sorry. So here you see, now we've retained in the text dump, we've retained the x's and the y's, but you can basically see everything there. But most importantly, look towards the bottom there. You can see the type. So here, variable. There's a variable list here which has in it a dictionary where x is a float and y is a list of integers. Okay. So, and then Parquet is incredibly useful because it's so simple to use. Parquet is, I suspect, a very complicated library with lots of optimizations in it. But the wonderful thing is that as the user, you basically tell it to write all your data out and read it in, and everything else is magic. And it's magic in the way that magic is supposed to work. Doesn't go wrong. Okay, so there you've written it to a local file, and then we can just read it back, and the array comes back exactly as it was before. Okay. All right, so ragged arrays is another name that we have for these. So this is taking, I believe this is exactly that same array that we were looking at as the very first example that I had. So let's set that. So you ought to have this in your workbook. So definitely load that up, because one of the disadvantages of this screen is that it's going to disappear, but we're going to need to refer back to it. Okay, so let's talk about slicing or indexing. So here we're going to do the 3, 1, -1, 2. Okay, I don't know about you, but this hurts my brain. But let's see if we can do it. So let's see. Okay, I have to memorize this. You all help me, and you should have it written down. The 3, 1, -1, and 2. Okay, so if I go back, all right, for the 3. So the 3 is the outer index. So this would be the 0, the 1, the 2, the 3. Okay, and the next one was a 1, right? Okay, so which one will be the 1? Second one down, so it'll be this guy. And then what was it? It was a -1? Is it -1? All right, so what is going to be the -1 in this? Sorry? This guy? Right? And then what was the last one? Was it 3? 2? Okay, so 0, 1, 2. So that slice should be 0.726. Okay, did we get it right? Pretty sure that's right. Yes. Okay, and then there's slicing. The only difference between slicing and indexing is like a slice that only returns a single scalar, and slicing is a slice that returns an actual list. All right, let's see, can we do this one? Okay, ragged is 3, 1 colon, -1, 3 colon 1. And you can start to see both how powerful this is, and also without some aids, how hard it can be to interpret. Okay, so let's go back. Okay, so it was 0, 1, 2, so it's the same thing, and then it was 1 colon, right? Is that right? So 0, so what does 1 colon mean here? Sorry? Right. Well, so we start indexing at 0, so it'll be the second element, or 1 plus, so it's these two. Okay, the 1 colon. I can't remember what the third index was. Could someone tell me? Sorry? -1. Okay, so what does -1 mean? Right. But we're looking at 2 arrays here. So that -1 actually refers to this dude and this guy right here. So these two things. All right, and then someone remind me, what was the fourth? I'm sorry, somebody has to speak up. Is it 1 colon 3? Okay, so 1 colon 3 is going to be, so 0, uh-oh. Yeah, but okay. Okay, so 0, 1, 2. Oh no, wait. It's 1 to. Okay, so yeah. So it's 0. Not this guy. So it's going to be -0.54 and 0.726, and here it'll be -0.199 and 0.827. Remember, the 3 is like the beyond the end. Sorry. Yeah, okay. Yeah, so I had a panic moment there because I was thinking 3 in the wrong way. All right, so we should get the 054 and the 726 and the 199 and 827. All right, let's see if I screwed up. Okay, I think I got exactly what I predicted. Yes? Will it blow up? The really awesome thing about, Jupyter Notebooks is that we can do something like, oh, that was advanced slicing, so I think this is right. So AR equals AK.array, 0, 1, 2, okay, can't type. All right, let's make sure that came out right. Perfect. And now if I do something like, let's say 3 colon, we'll get a 4. And let's say I do a 3 colon 5. So now I should go right off the end of the array, right?
That's how it works. I didn't think that's how it worked in NumPy, but I just tried it and it works that way in NumPy.
I was just going to say we could try it in NumPy, but thank you for already trying that. But
The first one, if you put the first one.
yeah, that's right. If we did 5 colon 7.
Oh no, you just get it.
Mm-hmm. And does that work the same in NumPy? I believe it does. It's meant to. I would call it a bug if it didn't happen.
I mean, I thought.
Yeah, ArcWord is meant to have the same semantics as NumPy. So when you learn these little things in NumPy, they should also be correct in ArcWord. All right. Okay, and then now advanced slicing. Have you ever done the slicing with the false, false, true, true? I bet you can almost guess what that's going to do, right? Remember there were 4 things in ragged. It'll ignore the first 2 and it will love the second 2. In fact, this, false, false, true, true is what you use when you you do something like, your array open bracket, array greater than 3 close bracket, right? To select out all the array elements that are larger than 3. So when you do that for NumPy, it generates an array of falses and trues, which then can be applied here. So you can use that, in awkward, it's exactly the same way. Whoops, sorry about that. Okay, so here, again, if we went through that same exercise that we did before, we would have come out with the -384 and the 827. All right? Kind of makes sense? So as we were just learning, and thank you for your help there, this works both in NumPy and in awkward. The advantage, of course, being in awkward when you have these hierarchical data sets, you're not, you don't have this huge piece of three-dimensional memory. Okay, great. And actually, we were just talking about how this might work. So look at what happened here. So we took that ragged, which is this humongous array that's multiple levels deep, right? It was 4 levels deep because we're using four things for the slicing. And we asked greater than 0, and it broadcast that operation all the way down to the actual elements. So if we were to get rid of the dot, dot, dots and print this out in all of its glory, you would see that there was a true or false for every single floating point number that was in that ragged array. And if you think about it, this is exactly what happens in NumPy as well. You would end up, when you did something like this, the broadcast down to the lowest level. And then we can just use the true-false thing I just showed from the advanced slicing, and we can. I'm gonna remember to do it properly. But now we can eliminate the elements that are negative. So those elements have just been erased from the lists and removed. Okay? And it's exactly as you would have done with NumPy. Okay, so we've already talked in NumPy about various reductions like mean, for example. And the beauty is that they take an array and they turn it into a single number. Like mean will take a list of numbers and turn it into a single number. Awkward is no different, but you got to think a little bit about what array in ragged do you actually want to be summed? Do you want one of the low level or the lowest level arrays, one of the higher level arrays, because you might have some arrays and some lists of numbers, things like that. So this is where this access argument comes into play. So if I just do a sum, it added up, it went through that array, treated it as just one long list of numbers, and just added it. So it went down to the very bottom, and it did it for every single number. But we could do, okay, anybody care to take a guess at what axis -1 will do? What does axis -1 mean when it comes to this mess? Yeah. Yep. The innermost like that, for example, or that or that or that or that, right? Okay.
Yeah, so axis here, you can think about like the nested level, right? So this actually ragged array, it has some levels of nested. We're gonna go and take the deepest level of nested and do the sum there, and it's gonna ignore the other levels. Maybe some of these, there is this deepest level, maybe in some other elements there is not the deepest level, right? So some of these will be summed up, some others are not going to be summed up, but it depends a little bit where, how the deepest is defined.
Yeah. This example was chosen to be relatively uniform to try to avoid some of those questions that you're bringing up. But
Or that exception basically behaves the same way on NumPy. If you were using like -1 as a axis, you just went
Yes. Okay. So let's do this. All right. So here you see, so for example, 3 levels in the 2.16. Let's see if, oh, sorry, I hit a magic button and I lost the, okay, so, oh, beautiful, came back right where I needed. Okay, so 2.16. So if we add the 1.84 together with the 3.24, we should get that that should total up properly. Does it? Well, it's a, yeah. But there, okay, there must be, in the printout, there must be significant figures cut off. That's why the 4 is missing. Okay, so yes, they add up. All right, great. So that 2.16 took that innermost array, turned it into a single number. Notice that it didn't pop it out one level here. It left it as an array. Okay, and then we can also do sum ragged axis equals 0. So what is that going to give us? Will it give us a single number, kind of like the first sum? Or will it give us sort of a sum for every single entry in that top level array? So there are 4 in ragged, right? The outermost axis, there are 4 levels. Let's see what it does. Oh, sorry. There we are. Okay. So there's the 1.56 and the 0.58. Where are those numbers coming from? And it's still 3 deep. This is really hard. Okay. Can I go back? Whoops. All right. So the 1.56 you would get by summing that guy with this guy, with this guy, with that guy. So it's like down the axis. So axis 0, right, is picking 1 from each one of these guys. In short, did I get that right? Yeah. I'm always nervous I get this one wrong because this is very hard to interpret.
This is 6, so it's worth seeing a little bit the output. It says 6 times var, and this is number 6 because the first element there, it has 6.
6, right? 1, 2, 3, 4, 5, 6, right?
That's the longest we have. The others do not have 6, less, blah, blah, but it's behind, but what's the longest, right? Same thing with the -1, behind, like, what's the difference?
That's a really good way to look at it. I just sort of ignored the 6 when I was doing the calculation to make sure I understood what was going on when I first came up with the example. Okay.
I think worth from this keeping in mind that -1 is like usually what we need. This axis -1, this is what we need most of the time. We are
Right.
working on this in our project as well using this. Because usually if you see the data structures, you usually want to sum up the deepest level as that. So keep in mind the -1, that's useful.
That's a good point.
That's usually
When you're analyzing the data, often what the hierarchy tells you, what each of the final list of numbers you're looking at is. Like, it's okay. I'm going to use an example from my own field because it's the easiest for me to come up with. But it's the energy of all the electrons in a particular collision. So I want to sum up all of those. I want to sum up all of those guys to find out what is the total energy going on in my collision. But I want to know about every single collision. So the axis -1 will take care of that. However, as you can see, you can get way more sophisticated. Yes?
Just out of curiosity, so if you did like access equals -4,
Okay, so the question was, if you take this sample and you do an axis of -4, you get the same result as an axis of 0. Is there a reason why you would say 0 instead of -4, for example? Okay, so two things. Usually, when you're analyzing your data, you know exactly what the structure is. So I would really recommend using whatever is going to be the most readable, and it's almost certainly not going to be the negative number. However, there are times where you write an algorithm to process the data, and you need it to be, or you would like it to be generic, because it's not just going to be used on your particular picture of the data, but also something that's more arbitrary. And in that case, it may be you're much more interested in knowing, in being up some levels from the deepest level. And so then the negative numbers make sense.
What's going to happen if you put -100?
Finally, an error. Okay, but yeah, excellent question. And it comes down a little bit to style. But if you are positive of what your data shape looks like, I would say use a positive number for your axis personally. But if you're writing a function which is going to massage some data, and it might be called with several different types of data, then it may well be the negative makes much more sense in that particular case. Sorry? Oh, yeah, of course. Yeah. Oh, sorry, yes.
I was wondering, in the previous, how would you read that information in type?
You mean this?
Yeah.
Okay.
Use that information to assume.
Right, so 1, 2, 3, 4, 5, 6, right? And then inside the next one, it's a variable number. And then inside there, including 0, and then inside there, it's a variable number, and then everything is a float 64 that's in there.
So then from there, we'll be able to tell that the deepest image is 4.
Yes, yes, yes. Yeah, yes, and if you have something where they change, it will show up in a much more complicated type expression here. Okay? All right. So how are they even defined? Okay, I apologize. I thought I'd gotten rid of that, but hopefully this isn't an old version of the tutorial. Okay, so here the summit axis 0 is coming straight through, as we said, and then axis 1 straight through, and then you have to sort of extrapolate for higher dimensions. But this is the way to think about it, and that was what those examples that we just went through did. Maybe because this is graphical, it's a little easier to understand than the arrow pointing that I was doing before. But right, so axis 0, this is the really weird one. So there you see the 17, 10, and 4, and exactly how they were summed pictorially in that picture. Okay, which matches with what we were doing with the ragged array when we went through with axis 0.
So it's almost like it broadcasts them.
Yes.
And it fills in with
Yes.
with blank.
Yes.
And it's always kind of left shifted. Like it keeps the, like the list, it keeps the elements on the left side of the list, or the early part of the list, I guess. It just pads, I guess, is a better way to say it than broadcast. Pads everything with blanks, with NAND.
Oh, now I understand what you're saying. You're talking about, like, for this guy, for example, this padding. Yes. Yes. No, that's right. That's right. It effectively skips over it, pads it with a 0, but it doesn't actually, it's not necessarily a 0. It'll really depend what the operation is, but yeah.
Yeah, maybe you want to tell us more. But if you put zeros there, you will have a bigger memory footprint than having nothing.
Yeah.
Yeah.
As far as it's just like a placeholder
Right.
that says, this is a NAND, or this is
Yeah, no, that's right. That's right.
Yeah, that's way more efficient than massive.
Yeah. Oh, yeah. Very. It still has something there. That's exactly right. Yep. And you know, this is the reason, like in my field, we don't use NumPy, we use Awkward. Although under the covers, Awkward is using NumPy, it's just not in the full n-dimensional representation, but it uses many of the same kernels. The implementation is a whole different thing. Okay, great. Okay, let's do let's look at something slightly more hierarchical as opposed to the straight up just nested lists that we were talking about before. All right, so we can do element-wise formulas. So here we're going to take, this should be familiar after the demos that were done. I guess that was part 1, looking at the lengths. So we're going to take the structured points and x. So you can almost guess what that's going to be, right? Can I just do this quickly? Why does it go back to the? There's a trick. Okay, so if I create a new guy and do structured points x like that. Okay, so you see the 5.27, the minus 3.51. If we go up and we look here, the 5.27 right up there, and then the next one is the minus 3.51. So we just used array slicing that we are so familiar with in NumPy, and we just picked those puppies right out of there. We really, it just works, even though we have a rather complicated hierarchical data structure. We have just, in that short little slicing, we have picked out all of the x points. Okay, so weird that it won't. Okay, any rate. Okay, so let's take the square root of all of that, the square root of the addition, and there now we get the actual distance from 0 for each one of those, for all of those points. Note below a nice shorthand. I don't know about you, but always having to type open bracket, double quote, right, comma, double quote, or something like that in this particular case is a little bit of a pain in the rear. So Awkward understands this shorthand where you can use points and x and points and y. Unfortunately, if you're using a high-end editor like, say, VS Code or PyCharm or something like that, the IntelliSense won't work in this particular case because these are, right, that's taking advantage of the get item. Let's not, sorry, I shouldn't, any rate. But you get the same exact thing for that. So it's just a nicer way of typing. It's syntactic sugar, if you will. Okay. All right, so let's do the first. Sorry. First quiz. No, that's more than scrolling up. See, it's more than that. Okay, so let's do a quiz. Let's take the data, which is this movie array, and what I want you to do is select out the movies that don't contain Bruce Campbell as an actor. He's famous for Evil Dead. That's where he got his start.
I think we have a slide.
Yes, we do have a Slido. Okay, this should all be in your workbooks. This shit drives me up a wall.
Alt tab to go to the slide.
Wow. No idea what's going on here. but I know about the Alt tab. I was the one that taught you that.
Yeah, but if you want to go to the slide, you think you don't need to run it yourself.
Right. No, but I have to turn it on.
Clear, not clear.
Yeah, I know. I know, man. It's not my first rodeo. Okay, we've got the Slido running now. But they're good questions.
And then I think after that we can skip the rest and just go to the project.
Think I should do that? Here, wait.
Let's see the rest.
Yeah, exactly.
This is not needed.
Combinatorics.
This is
No,
bonus-
not needed
bonus.
for the, yeah,
No, that's a bonus thing.
okay. Good idea.
That's what I said.
Yeah, no, that's a good idea.
And you'll note there was a hint about the ak.all, and which is like numpy.all, and ak.any, which is just like numpy.any.
All right, a couple people got it.
Anybody need some help or advice? Just raise a hand and we'll walk around. All right, give it maybe another minute, and then we'll start working through it. See if one more person gets it. All right.
Okay, somebody who got it, could they just quickly outline the strategy they used to get this?
I don't know who it was that got it, I just know that 8 of you got it, at least. Were you raising your hand?
I'm scratching my head.
Oh, you're
No one's
scratching.
raising their hand already. Sure, yeah.
Just speak up so everybody.
All right, so the first thing that I did is try to figure out how to make a Boolean of is the actor Bruce Campbell or not. So I did data and then actors in the first index. So data square brackets, actors, comma, colon, which maybe wasn't necessary, I don't know. And then I did either not equals cannot index a ragged list with a janky array or something, jagged array.
Jagged, not janky, jagged.
Yeah, so then I had to flatten that, so to do that, I did ak.all, which was if I had done not equals, then they had an all not equals, so that worked. Or I did ak.any if I did equals equals, and then I had to invert that in that case. Yeah, and what basically all that gives you is like 6, and it's either true false for the 6. So then you can use that to index the
So
first.
the strategy is, look at all the actors, do true or false, depending upon the actor is Bruce Campbell or not. Then ask if any of those interior lists have a Bruce Campbell, or true or false, depending upon whether you're doing equal or not equal. And then use that as a filter on the list of movies.
I think that's that is you did it and you just outlined it in way more detail than I did, but at a high level, I believe that's what you did. Okay, so what the hell is going on here? Sorry, folks. I'm having, so, we have a friend that we work with who swears by this tool. And so we're like, okay, because we pulled it from others as well, the parts of this tutorial. So we're like, okay, we'll just use what they used because they were successful. Okay, so is Bruce Campbell? So data.actors double equals Bruce Campbell. All right, so let's run that, and we should get this list that you were talking about when you do the equal equals. All right, so there's a Bruce Campbell. This one was Evil Dead, if I remember correctly. I don't remember what the others were, but he's there, not there, he's here, and not there. So I think there's 2 that he's not in. So now the thing is that we have, for each movie, we have a list. All we care about is there any true in here? And so here we do ak.all, not, the tilde is ak.not or NumPy.not, is Bruce Campbell, and on this inner axis. We could have used an axis equals -1, but we know our data structure, so we're going to use axis 1 because that makes it clear. You don't have to think, it's always axis 1, so we'll use axis 1 here. But that's a matter of style, not programming correctness. And so this, as he was saying, gives us a single list of falses and trues, right? And so here are the 2 movies that we already determined where Bruce Campbell just didn't get out of bed. And so we should just get those 2 movies when we do that one. There. So a simple plan and drag me to hell. Okay, does that make sense? All right, so there's a section here on combinatorics, but I'm going to blow it off. It's you're welcome to look at it at any time. In fact, this whole thing is in GitHub, and the reason I'm going to blow it off is I want you to start playing with taxi cab rides in Chicago, the great city of Chicago, which is my favorite city here in the United States, despite me living in Seattle. But at any rate, so we'll ignore this. Combinatorics are extremely useful, just not for the project, and we're running out of time a little bit. So I'm really, really going to skip it. Okay, so take a look at the taxi ride. It's a hierarchical data set, and you're basically having to do something similar that you had to do previously, which was calculate the lengths of the taxi rides. The data is also messy, which makes it more exciting. Okay, and if I remember correctly, you can get the solution in a single line.
It's a huge notebook. You will see the notebook is big, but it's
Right. Most of the notebook you're just going to just motor through because everything is provided for you. And then at the very end it says, well, now that you've been lulled into a great sense of contentment, here's a cliff. Drive off it. All right, it's not that bad.
And you realize a lot of times, you spend more time to understand the problem.
Or clean the data. Okay. Yeah, the first part gives you some lessons on how to load the data, but that's not germane to the solution. Right. What we'll do in order to try to keep everything on time is around, unfortunately, only 15 minutes from now, which is 5:25, we'll quickly go through the solutions. And in fact, you can kind of see it so this is a repeat of what was in the problem statement, and this is just the for loop version, where you pick out a particular, taxi cab number 75 and the second from last ride, which was this particularly interesting taxi cab ride. But you can see right here is +1 versus, I +1 versus the ith, right? So there's that difference that we were doing in part 1. The square root to calculate the square root of the sum of the squares to calculate the total distance, and then summing the total distance. So now that we've been thinking about arrays and thinking in terms of arrays a little bit, you can almost start to map these into array operations, both familiar and also, well, no, I guess they're all pretty familiar. It's just in a much more complicated data structure than what we've done before. Okay, so here's the solution, which, you know what? Okay, can I just split the line up here so that, that was not, sorry. And I think there. Hopefully that's a little more readable at this font size. So here is the first subtraction for the kilometers east, right? And then the north there, right? And then here the square right there, and then the square root, and then of course the sum. But if you just did the sum without the axis number, you'd be in a little bit of trouble, right? Because it would just sum everything. So you really want it to just sum at that deepest level, which is the trip level, the per trip level. So the axis -1 got used there because, frankly, we were being a little lazy instead of giving an actual number there. All right, so if we do that, so all 350 of them, and then it's var because the different taxis took different numbers of rides, right? And then a number. And so we can just see here. And the really nice thing is that where some of the data was blank, we were able to just clear it through. We didn't have to actually mess with this. Although if we are now to start plotting it, we would probably need to be doing some filtering to make sure that it looked okay. Okay. And then, right, good point. And so here, as a nice check, we did that 175 minus 2 by hand, and it came out to be the same. All right. So there's a bunch of other solutions in here, but given the time, we won't go through them here. But I just wanted to thank you all for coming, and hopefully we broke your brains, but not too badly. Got you to think a little bit more about these array data structures, not just as single independent rows, but starting to think about these as much more powerful, potentially much more powerful data structures, and at the same time, hopefully, maybe a little bit leveled up some of your array skills and introduce you to a few new libraries. We are going to be around you're around the whole week, right? Yeah, we're around the whole week. Feel free to just buttonhole us and pick our brains about anything. Wherever you see us, we love talking about the stuff that we do. So it's mostly hard to shut us up, but please feel free. And that goes also for the others who are helping us out. There's Matthew in the back. Just wave your hand. And then actually Jim Paversky, who just arrived, he is the primary author of the Awkward Array library. And he would be more than happy to talk about this stuff, as would Angus. But short of that, you made it through 8 hours. Congratulations. Relax a little bit. Let your brains reset before you do it again tomorrow. All right, thanks everybody.